Hello class, welcome to our second video for reason and rational decision making. This video is directly related to the quiz for this week. I've based it both upon what Robert has written up in the quiz questions and on what we've read in the book so far. So basically everything that you need to know for the quiz will be, well, I suppose everything that's in the video will also be covered in the quiz, though there's some other questions that will require you to have done the reading as well. Okay, so what we learned this week is about categorical logic, which is Aristotle's formalization of logic. It is the first formalization of logic that we know of from the Western world. It was likely developed by many people in Plato's Academy around the same time, but Aristotle is the one to have written it down in the posterior and prior analytics and among some of his other books as well that we have left. It is still a very helpful form of logic because it introduces us to the very beginnings of analytic deduction. And so what's important in categorical logic is something to do with our subjects and our predicates, and something to do with our existential import, and also something to do with our inferences. Now I'm going to go through all of these ideas, our inferences, our existential imports, and our subjects and predicates. And I'm also going to talk about the way in which we formalize this, which is with our square of opposition here and our Venn diagrams here. Now you'll notice that I've pre-written everything on the board, and I'll step to the side just to give you a full view of everything that I'll cover in this lecture. And I've done this just for the sake of saving time. I'll also post a picture of this board on the Canvas page. I might also just freeze a frame of it close up in the video that I post. Now, I recognize that it may not all be easily readable, but I'll be speaking it out loud, and I'll also have the picture online so you can use that for reference. Hopefully that's enough. And if it's not, please be in touch so that I can structure my future lectures accordingly. Okay, so subjects and predicates are where this section begins. It's also where your quiz begins. What's the difference? So in our basic grammatical structure of sentences, of claims, of propositions, we have very basic units called subjects and predicates, and also copulas. And our subject is just a named thing. A subject is an entity that takes up predicates. It's a person, or it's a thing, it's an object, a place, maybe a time or an event. Our subjects are the proper nouns of our everyday communication. Now, a predicate, on the other hand, is a property or an attribute that we apply to the subject. So, for instance, on the board, and we'll use this later, but for now it might be a helpful illustration, that Oinky is a pig that flies. It says Oinky is a pig that doesn't fly, but for this example, let's imagine that Oinky is a pig that flies. We're looking at this proposition, this sentence, and what we find is that in the sentence there is a subject and there are two predicates with a copula that connects them. So our subject is the named object, the person, the thing, in this case the pig. It's Oinky. Our subject is Oinky. Now Oinky has certain properties that describe or define or tell us who and what the proper noun, the name Oinky, the subject, is, which is that Oinky is a pig and Oinky flies. Okay, so our subject is Oinky and our predicates are pig and flies. So Oinky is a flying pig. Flying pig could be another way of bundling up the two predicates into one, being a flying pig. Now, the interesting sort of connection is our copula, which is our, in propositional grammar, the glue that binds together subjects and predicates, the connector word that brings together the properties under the heading of the proper name of subject, or the flying pigginess, and that being a description of Oinky. Okay, So the copula in the sentence, Oinky is a pig that flies, is the word is. Is brings together our two properties with the subject Oinky. You get the picture. Okay, so these are subjects and predicates. And when you're doing your reading and you're looking at these Venn diagrams, what we should be thinking is that S and P's don't mean subject and predicates. Really, we could use any letters we like. We could say that this is an X and that's a Y, or this is an alpha and this is an omega, whatever. It doesn't matter. These are just variables. And S and P are the variables that are used most commonly in textbooks, and it's just helpful for consistency in writing and communicating and test taking and stuff. But you should be sure to remember that S and P are variables. They don't stand for subject and predicate. Really, they're both just predicates. They're both mapping out properties. But the reason that we use Venn diagrams is to discuss the existential import of our statements. And so we read about this in, I believe it's section 4.2 from your book, where existential import is when we state things, when we give explanations, we use propositions like Oinky is a pig that flies. Implicit in our statements are often existential claims, like there do really exist these things that I'm talking about, or alternatively, if I were talking about this thing, if there were a thing that exists of which I'm talking about, then that thing would also have these properties. So that's a whole bunch of logical language, might be a bit jargony. Let's give an example. So for instance, if I were to say taxation is theft, right? Now I'm not committed to this view, just as an example. Taxation is theft. So all politicians are thieves. Okay, so what I've done is I've given a universal statement. I'm talking about everything that is a politician is also a thief. So we'll notice that these are both predicates. Anything that has the predicate or property of being a politician will also have the predicate or property of being a thief if my statement's true that all politicians are thieves. Okay? However, I haven't indicated that there is anything that is a politician. I've just set up a hypothetical category, an inference, that if there were something that was a politician, then that thing would also be a thief. Okay, so we find that in our in our universal statements, our statements about all or none, because if I say that there is no such thing that is a politician, I'm saying of all of the things that there are, none of them are a politician. It's a negative universal statement. So in all of my universal statements, all I've done is set up this sort of hypothetical conditioning that if such a thing is a politician, then it's a thief, but I haven't implicated myself in the existence of anything to which that relation holds. There's no existential import in my universal claims. It could be the case that even if all politicians are thieves, there's just no such thing as a politician. All unicorns have horns. That could be a true relation, and it's a universal statement, but there are no such things as unicorns, and so we can't hold there is no existential import in the relation between my statement and the actual existence of a thing that's a unicorn, and it therefore must be having a horn. Okay, now our universal statements are different from our single statements. So any sort of statement that has to do with a sum or an indication of a certain class, but a member of that class. And so what I mean by this is if I were to say that some swans are white, or there is a swan and it is white, insofar as I make these kinds of statements, I'm no longer talking about universal hypothetical relations. I'm talking about actual things that have actual properties. So if I say that some swans are white, what I've done is unlike in the universal case again. I've given an existential import to my statement. Implicit in what I've said is the notion that something exists that has the property white. So there is some swan that is white, is what I mean to say when I say that some swans are white. And we'll notice this in our formalizations of categorical statements. So according to Aristotle, there are roughly, or in fact exactly, 4 kinds of propositions. And all statements, all sentences, all claims can be described as having or taking one of these 4 forms of sentences. And these are A, E, I, and O sentences. Now, an A sentence and an E sentence are both universals, and I've alluded to these moments ago. They're universal statements insofar as they are positive, that all things that have this property will also have that other property, or they're negative universals, which is to say that no things that have this property. So of all of the things, no thing that has this property also has that other property. Okay? And these 2 statements do not have existential import. Now, our bottom 2 statements, our bottom 2 categories of types of sentences or propositions, our I statements is that some S's are P's, some swans are white, does have an existential import. What I'm doing is I'm indicating that there exists some S or some number of S's or swans that are white or that are P, right? And so I am indicating that the truth of my claim depends on the existence or not of the objects or subjects to which my predicates, being a swan and being white, would hold true. And likewise for O statements, this is again in form the same as our universal statements. We have positive universal, negative universal. We have positive existential and a negative existential, which is to say that in an O statement, some S are not P, so some swans are not white. And the truth, again, of this statement depends on the truth of the implicit existential import of it, which is that there exists some swan that isn't actually white. Whereas these don't depend on any sort of thing existing to make them true or not. What depends, what they depend on for their truth is rather the hypothetical coherence of the predicates. So if I were to say that everything that's a square is also a circle, that would be a false A statement because it's impossible for the square to also have the predicate circle. Now, we see this represented here in our square of opposition. Our square of opposition is a sort of more, it's a modern formalization of Aristotle's A, E, I, and O, just like the Venn diagrams are. Again, I recognize that the writing is probably small, but refer to the picture that I'll post for this. We have A's in the upper left, we have E's in the upper right, we have I's in the lower left, and O's in the lower right. And the reason that we formalize it this way is that we can see that given the truth values or the true or falseness of any of these particular statements, that they're going to have to hold certain sorts of relations to one another just so long as they have the same S and P form, which is to say that they're talking about the same predicates. If we're talking about different predicates, then we can't compare the I's and the E's and A's and the O's. Our sentences have to be of the same logical form or to involve the same logical operators in order to compare their logical form. Okay, so if an I statement has the same truth value as an E statement, then they'll contradict. Right? So if I say that some S or P is true, and I say that no S or P is true, then I have a contradiction, because what I've said is that there is some S that's a P, and I've also said there's no S that's a P. These are contradictory statements. I can't hold both at once. And we see the same relation between our A and our O sentences, where all S is P and some S is not P. I've just said that everything that's a swan is also white, but there are also swans that are not white. That's a contradiction, right? And so we formalize our categorical statements into the square of opposition in order to help make our inferences quickly or faster, in order to see the way in which inferences work together. Now, we also have a horizontal and a vertical relation between our categorical statements. This is less important. We're not going to test you on this. It's more important to know that these statements are going to be contradictory, but it turns out that A and E statements can't both be false, but they could both be true or have different truth values. And likewise for I and O. So our horizontal relations can't both be false, and for our vertical relations, both can't be true, but they could both be false or have different relations again. Now, this is important. Like I said, you won't be tested on it, but it's important tangentially, because when we move on in the next unit to truth tables, we will deal exactly with this issue. So we find that these sorts of statements, when represented in terms of their truth values, will represent very similar form in truth table formalizations. Now, this is just because all of deductive logic holds together analytically, which is to say that it's just a complete set of formal logical relations, that the way in which reason is axiomatized in this system and in the next system that we'll be looking at, this being categorical logic, and the next system that we look at is propositional logic. They use the same exact forms of reasoning, of coming to conclusions, of thinking about propositions as of deductive or deductively, and we find relations that are just the same, though said a little bit differently, or put in the form of a square or a bunch of circles, or in the form of a truth table. Again, we'll get to that next time. So let's talk about Venn diagrams. So our Venn diagrams are our Venn diagrams are representations of our categorical statements. Now, when I say that all S is a P or no S is a P, again, I'm not making an existential claim. I'm not saying that something exists that has a certain property, right? Rather, what I'm doing is saying that there is a certain class of objects that can't or must also hold a relation to something else. So when I say that all S is a P, what I have in this first circle is the objects that are S. Every single object that exists in the whole world, in the whole universe, that is an S, that has the property of being S, maybe of being a swan, right? Or I suppose to stay consistent with my examples, is a thing that flies. So I have two predicates here, S's being a thing that flies, P being a pig. These could be anything, right? It could be S is a swan and P could be is white. But let's use S being a thing that flies and pig being P as our predicates. So S is the entire world of things that fly. And P, this circle, is the entire world of pigs. And if I say that all S is P, what I'm saying is that everything that flies is also a pig. Okay? So this is everything that flies, and this is pigs. Okay? Now, there are going to be certain pigs that don't fly, right? And they live in this area, right? Those objects, those pigs that don't fly, would live in that area. But everything that flies is also a pig, and that would live here too. It would live in the middle, in between, where both predicates are shared. And what we want to do to represent this is to say, well, all things that fly are pigs, is not to draw the conclusion that there exists a thing that's a pig that doesn't fly, or the conclusion that there is a thing that exists that's both a thing that flies and a pig. Rather, because there's no existential import in our universal statements, what we're going to claim instead is that it's impossible for anything to exist here, and so we shade it. And likewise, we will shade for negative universals too. So take this as an axiom. When you see a categorical statement and you're doing Venn diagrams, and the categorical statement is a universal A or E statement, we're going to be doing shading. Okay, so universal statements require shading. So it's impossible for something to be an S without also being a P. That's what we say in our A sentences. Now in our E sentences, we're also making universal claims. We're saying that no S's are P's. It's impossible for something to exist that has both the predicate S and P. So nothing can live in this overlap. There's nothing that lives in the world of both S's and P's. Now, it might be the case that they're S's and it might be the case that they're P's, but all that we've said with our categorical statement is that it's logically impossible, if this is true, that there is such a thing that is a pig and that it flies at the same time. Now, our I and our O statements, our existential statements, operate differently. We are no longer talking about oh dear. We're no longer talking about hypothetical logical relations. We're talking about things that exist. We're saying that there exists some S, something that flies, that's also a P. And insofar as we're saying that there is some S that is a P and our statement has existential import, we're not going to be shading because we're not talking about a hypothetical logical relation. Rather, we're talking about an actual thing. So if some S is a P, what we're saying, given our existential import, is that there's some being, some subject out there in which both the predicate S and the predicate P inherent or are a part of, right? Oinky is a pig that flies. Oinky would be our subject that exists at the intersection of our S and our P. And so rather than shading, what we're going to do is draw an X to say there exists something, and that something has both properties S and P. Now, our O statements are similar. We have an existential import, and what we're saying is that some S's, so some things that fly, are not pigs. So all we're saying is that there exists some S, there exists some things that fly that are not pigs. And we're not saying with this sentence that there are no pigs that fly, or that there are only pigs and nothing flies, or whatever. Rather, what we're saying is just that something exists that isn't a pig but it flies, maybe a bird, right? And so what we get with our existential claims is the indication that there is at least one thing that has these properties, and what we get with our universal claims is that it's impossible for any subject to have these kinds of properties, either both S and P, or just an S, or just a P. Okay, so what we can do by using our new square of opposition, or likewise our Venn diagrams, is take everyday regular sentences and find out what we mean by them, or what others mean by them, or if, given what someone has said, whether their inference is valid. So we can take the logical form and extract it from the sentences that are being used, that we use, that others use, and we can analyze it. We can look at it and say, well, does that logical form really imply what the person or myself thought it implied? And so this is a question that comes straight out of your quiz. And we have two statements here. and I'll read them out loud for you because, again, I recognize the text is small. 1, it's false that some recreational drugs are good for your health. And 2, therefore, no recreational drugs are good for your health. So when we're looking at inferences, we're not just looking to categorize our statements. Rather, what we're doing, as we do here, right? Rather, what we're doing is looking to the categorization of the statement in addition to its truth value. Now, we can categorize a statement, and then we can say whether or not it's true or false. And then, given that it's truth or falsity, we might draw a certain conclusion. We might infer from the truth or falsity of our statements some further statement. Okay, so if I say that it's false that some recreational drugs are good for your health, we should notice at once 2 things. We should notice that there's a statement about the truth conditionality of our number 1, and we should also notice that there is a sentence that takes the form of one of our categorical operating sentences, which is that some recreational drugs are good for your health. Okay, so if I just break those apart and I take them as 2 separate things, we can begin to break down the sentence. So let's start with the categorical part, which is that some recreational drugs are good for your health. Some recreational drugs are good for your health takes the I form. There are some S that are P. Some recreational drugs good for your health, where S is a recreational drug and P means good for your health. Okay? Now, we would say if it were true that there exists something at the intersection of recreational drugs and those things that are good for your health. However, what we've done is we've said it's false. We're saying no S is a P. There's nothing, it's false, that recreational drugs are good for your health. Therefore, we're going to blank out our statement. Now, this is one way of doing it. It's a conversion way of doing it. I'll show you 2 other ways of breaking down or understanding the sentence. So what I just did was I took away the truth functionality and I took the categorical statement and I gave it its form, and then I thought, well, I'm not saying that some S or P, I'm saying that no S or P because it's false, so therefore adding back in the truth functionality and getting my actual conclusion. Now, another way that I can understand the statement is with our square of opposition. I can say that the I statement goes here, so I'm going to write a 1 to represent this, but it's also false. Okay? Now, I'm going to look at the conclusion, the inference that's drawn from our 1, which is that, therefore, no recreational drugs are good for your health. This is a E statement, no S or P, and our E statements operate on the opposite corner of the I statements on the square of opposition. And this one is our conclusion, our number 2 statement, is said as if it were true. It's not saying that it's false, so it's going to be true. So I'm going to write a 2 here, and I'm going to write true to represent its being stated as if it were true. Now, what we know is that anything on the opposite corner of our square of opposition can't have the same truth value. Our I statement and our E statement, our 1 and our 2 here, have opposite truth values, and so our inference is valid. And likewise, moving back to the Venn diagram, our I statement in my first example converted itself into an E statement. So this I statement became this E statement, so our inference is valid there as well. Now, I can also do it the following way. I can say that, let's say, for instance, all pigs fly. So this sentence is an A statement that all S is a P, and therefore these 3 dots, it just means therefore. Sometimes also symbolized with just a line between statements. It also means therefore. It's symbolization in deduction and logic. And it's way faster to write 3 dots than therefore. Anyways, so I have an A statement that all pigs fly, and Oinky is a pig that doesn't fly. Oinky is a pig that doesn't fly takes the form of an I statement, that there is some, an O statement. There is some S, which is Oinky the pig, that doesn't fly, that isn't a P. There's some pig that doesn't fly. Is this inference valid? Well, all pigs fly. So let's say I draw my 2 circles and I put my S and my P, my S being a thing that flies right here, and pig being a P. All pigs fly. Okay, so I have an A statement. If something is a P, then it's also an S. So there's no such thing as a P that's not an S. There's no such thing as a pig that doesn't fly, because all pigs fly. And so if something is a pig, then it also has the property of S, which means that all of the P's that exist, if they are to exist, live here in the middle. Okay? Now my conclusion is, again, an O statement, that there is a pig that doesn't fly. Now, when I do an O statement, I draw an X, given the existential import. And in this case, my existential import is that there exists some pig that doesn't fly. There exists a P that is not an S. And so for this, I would draw an X, right? I would draw an X where pigs exist, but flying things don't. Okay? Now, what do we see? We see that I've just drawn an X in a shaded region. And that's a contradiction. That's impossible. Because what my first statement says is that nothing lives here. Nothing can exist in this part of the circle, or 2 circles combined. And what I've said here is that something does exist in this part of the circle. And so, given that I have shading and an X in the same location, I find that my inference from the first statement to the next is invalid. And so these are just some ways that we can use categorical logic to determine the inferential validity or invalidity of our statements. We can find out if what we're saying is a contradiction or what we really mean. Do we mean that there's some sort of hypothetical universal relation that must hold between subjects, should they exist, who have these properties? Or do we really mean to say that there are things that exist that do have these properties? And if we are, then what sorts of inferences are we licensed to make given the existential or universal import of our claims? So again, when you're doing Venn diagrams, or you're reading Venn diagrams, or you're looking at them, if you're shading, we're talking about universal claims, our A's and our E's, and this shading implies emptiness. It implies that there's a non-membership, right? That there are no pigs that do not fly, that all pigs fly, if at all, given our statement here, right, that all pigs fly. Whereas an X indicates that something exists. It indicates membership. It indicates that there exists something that has the property P. There's some subject out there that has the property of being a swan, or there's something out there that is a pig, or there's something out there that flies, right? So we're talking about membership. And what we'll do next time is move on from the language of categorical logic to the language of propositional logic, using, again, the same forms of inference, the same forms of reasoning, and we'll formalize all of these sentences and all of these inferences into mathematical, logical operators. But for now, this is sort of our common sense, everyday language way of formalizing what we do, and in the next unit, we'll break it down one step further.